Assalamu alaikum dear students, welcome back to my channel. In last lecture we have talked about the definition of sets and how to write a set and what is meant by the order of or cardinality of a set. In today's lecture we are going to start with talking about some famous sets. So these sets are set of natural number, and sometimes it is regarded as set of counting numbers because you know very well we use it for counting purpose as well. And then we have a set of whole numbers with just one addition to set of natural number, and that is 0. Then we have a set of integers which includes whole numbers together with their negatives in except 0. Then we have set of rationals, which we say that a set in which elements are of the form p by q, where p and q are integers and q is non-zero, right? So in last lecture we talked about set builder notation. So this is how set builder notation helps us, because this is a set where we don't know the next element to a given element. Okay, if you are given a rational number, you are not sure what is the very next rational number, so we just exclude that expression tabular form. We write it in set builder notation because it takes the characteristic property of that set and just write it in the braces, right? And then we have the set of irrational numbers, right? So it is a set which contains elements like x, where x is not in the form of p by q, where p, q are integers and q is non-zero. It's very obvious, it is the opposite of rationals. Okay, and then we have set of reals, which is a union of rationals and irrationals. Okay, and then we have set of complex number, which contains set of real number as well as complex numbers. Okay, and then we have some special sets, set of even numbers, set of odd numbers, set of primes, and so on. So there are so many sets, but these are some of the famous sets that we use in our practice. So here we have another question which is of quite importance, because it is often asked in competitive exams. So the question is, why do we consider empty set to be a set, right? If I have not talked about this in my previous lecture, let me tell you that it is a set which contains no element. Okay, and it is either denoted by the phi symbol or it is denoted like this with braces and nothing in it, right? So why do we call it an empty a set? So George Cantor was a person who worked so much in the field of set theory. He can be considered as a pioneer in set theory. So the thing that convinced him to consider this as a set was actually the intersection of two sets, right? So if we don't include empty set as a set, then we will be entrapped in endless consideration of special cases. Okay, if you ignore it, if you call it to be not a set, then it will create so many problems for us. So it is better to consider it a set rather than just ignoring it. Okay, so now ladies and gentlemen, we are going to talk about the subsets. Okay, now the definition is very simple and quite understandable. It says that a set A is said to be a subset of another set B if every element of A is an element of B. Okay, like this. Here we have an example. We have a set which contains two elements, 1 and 2, and here we have another set which contains both elements of this set A, yet another element. We are not having any problem with that. We just need to have all the elements of A to be in B to call A as a subset of B, right? Then A is a subset of B, and symbolically it is written as A subset of B. Now this is the symbol for being a subset, right? And then there are two types of subsets. Number one is proper subset, the other one is improper subset. It's very simple. Proper subsets are the sets where all the elements of A are contained in B, and yet there is an element B belonging to B such that B doesn't belong to A. So B contains some extra elements other than the elements of A. Okay, here we have an example. By the way, this was also an example of proper subset. So all the elements of A are contained in B, yet B contain another element C which is not the part of A. So this A is proper subset of B, and symbolically we write it like this. We are just eliminating the line over here. Okay, so this is a proper subset. Okay, and then the other form is improper subset, which is obvious. It is a subset which contains it is a case where all the elements of A are contained in B, but B doesn't contain any other element other than the elements of A, so A is improper subset of B. Okay, so here we have another question, students, and this is also a burning question in the mathematics field for students. Why empty set is considered as a subset of every set? Okay, so the reason for this is very simple. It says that the reason is that there's only one condition for a set A to be a subset of another set B. And what is that condition? That condition is that all elements of A should be a part of B as well. If a set is not violating this condition, then definitely that set will be a subset of B, right? So if I talk about the set of empty set, then it doesn't violate. Can you find an element of empty set which is not the part of another set? Since there is no element in the set, so you can't say that the condition is being violated. That is why we consider empty set to be subset of every other set, right? Let's talk about power set, and its definition is very simple. Now, power set is a set which contains all possible subsets of a given set. Let's call that set as S. So if we talk about the set S, which contains three elements A, B and C, then its power set will be denoted by P of S, and it will be like this. You can find that every possible subset of this set S is included in this set, so this set is known as power set of S. Let us define equivalent sets. Now let me tell you people that it is one of the most important concept that we will use very often in group theory, so it's very important. Pay attention and listen it very carefully. Two finite sets are said to be equivalent if their cardinality or order is same. Okay, I'm talking about finite sets here. Keep this in your mind because the criteria for infinite sets is different. If you have two sets P and Q, find the cardinality of P, then find the cardinality of Q. If their cardinality or order is same, then they are equivalent. It's that simple. So as you can see that P contains three elements, so its cardinality is 3, and Q is also containing three elements, so its cardinality is also 3. So these two sets are equivalent. Okay, here I have mentioned, by the way, for infinite sets, two sets will be considered equivalent if and only if there can be formed a one-to-one correspondence between their elements. If you have gone through a course of set theory, you know this probably, so I'm not focusing on this so much because in group theory we mostly deal with the finite groups, finite sets. So we just need to have this definition in mind. That will help us very well. Here we have another important concept that will also be used very often in group theory course, and that is of equal sets. Now there is a difference between equivalent and equal sets that will be visible to you people now. So two equivalent sets are said to be equal if they have same elements. We have just talked about equivalent sets. In equivalent sets there is only one condition: number of elements in one set should be equal to the number of element in the other set, then we call that sets to be equivalent. Now we are implying one more condition, and that is all the elements should be same as well. Okay, if you rewind the video and go to the equivalent set definition we just talked about, there we have two different sets, yet they were equivalent because the number of elements were same. But in equal sets, it's not the only condition that number of elements should be same. The other condition is that elements should also be same. So if you look at these two sets A and B, they contain two elements, that is why they are equivalent, and those two elements are equal as well, they are same. So A and B are two equivalent sets. Okay, so there are few notes here. Order of elements may differ. Okay, this has already been discussed in our previous lecture, that order in two sets doesn't matter if you are trying to see whether they are equal or not. And the other is that in group theory, two sets, let's say P and Q, are proved to be equal by proving that P is a subset of